Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. In the last recorded lecture, I talked about the sequence networks, and we covered the sequence impedances of the Y connected loads. So now I will start with the transmission lines. So we will also now discuss the sequence networks of transmission lines, and also in this lecture I will talk about the sequence networks of rotating machines as well. But before starting with the transmission lines, let me quickly revise the contents of the previous lecture. So in the beginning I made the definition that sequence impedances are basically impedances that are offered to the sequence currents, and we have sequence currents, sequence impedances, and obviously sequence voltages. So together these constitute the networks. So we started the discussion with the definition, and then afterwards we discussed the sequence networks of the Y connected loads. So we took this particular case where we also considered that the neutral point of the load, Y connected load, is connected to the ground through the impedance Zn, and then we discuss the steps that are required for deriving the sequence networks, and the end result was that we derived 3 sequence networks, and we discussed that these 3 sequence networks are uncoupled networks. And some of the important observation that we made was that the impedance Zn, which is the impedance to the ground, so that impedance only appear in the zero sequence network. Also we observed that the positive and negative sequence currents, they only flow in their own networks, but these currents does not flow through the impedance that we called Zn. So through Zn only the zero sequence current flows. And we also made this observation that the product of the 3I node Zn, or basically in the network, because to the zero sequence current 3Zn is offered, but actually 3I node is the neutral current. So to the neutral current it is the impedance Zn which is offered to the neutral current, but to the zero sequence network 3Zn is offered. So we made these observation, and the conclusive point was that the zero sequence current, it only flow through the impedance to the ground. The other 2 sequence current do not flow through the Zn impedance. And we also mentioned this point that if, let's say, the neutral point is not connected to the ground, then in that case the phase voltage, VAN, which is the voltage of phase A to the neutral point, is not equal to VAG, which is the voltage with respect to the ground point. So in a unbalanced case, because then the zero sequence current will no more be zero, then it will not be the case. Obviously in the case of the balanced conditions, the zero sequence current is zero. So that's why it will still valid. But when we have an unbalanced fault, then this will not be the case. So then VAN will not be equal to VAG. So these were a couple of important observations that we made in the last lecture. Also we then solved a problem as well. So now as I mentioned in the beginning, that we have talked now about the Y connected loads, or the sequence impedances of the Y connected loads. Now we will start this lecture with the sequence impedances of the transmission lines, and then I will also cover the rotating machine. So now let's start with the transmission lines. So the case is shown here. Three phase transmission lines, where we are talking about the zero sequence currents, and it is mentioned here that this is basically, these are the three transmission lines. Let's say this is the ground point, where the potential is obviously zero, and this is the distance dn, which is the distance of the, let's say, transmission line to the ground. So as it is mentioned here that because the geometry of the transmission line, as we have already discussed before, that zero sequence current, it only flow through the impedance to the ground. The other two sequence currents, positive and negative, they do not flow through the impedance to the ground. So it is mentioned here that the arrangement or the geometry, it remains the same whether we have positive sequence current or zero sequence current. So the geometry remains the same. So that's why positive and negative sequence impedances are also the same. So same geometry is offered to the positive and negative sequence current. And if you talk about the zero sequence current, or about the the zero sequence impedance, then obviously the impedance to the ground is involved. So which is, we have already discussed, then we have in that case 3Zn. But here we are only basically taking the inductive reactance, so that's why it is 3Xn, and that is the X1, which is, let's say, the positive sequence inductive reactance. So even if you remember from the last lecture, you can look here, the zero sequence current was having the impedance, that is in the one phase, and then 3Zn. So situation is same here. The zero sequence inductive reactance is equal to X1, which is the positive sequence inductive reactance, plus 3Xn. And Xn, which is the impedance, the inductive reactance in this case to the ground, is equal to 2 pi frequency. This is equal to 2 pi frequency, which is 2 pi frequency, and this term 0.2 natural log of dn over d. So if one look here, dn is much larger compared to d. That's why xn is much larger. It's a much larger term, because dn is the distance to the ground from the transmission lines. So an approximation is made where z node is taken, z node is approximately taken as 3z1, and since we are taking only inductive reactance, so z node will be then approximately equal to 3xn. So for the case of the transmission lines, the same geometry is offered to the positive and negative sequence currents. So we take the positive and negative sequence impedances are the same, and then, as we have already discussed, that the zero sequence current, it flows through the impedance to the ground, and we have already discussed this factor 3 when we were discussing the Y connected loads. So now the impedance the zero sequence impedance will be a sum of x1 plus 3xn, and xn is can be determined from this particular expression, where both the distance among the transmission line and distance to the ground is involved, and since dn is quite large compared to d, so this term is larger compared to x1. So an approximation is made, and z naught, zero sequence impedance, is more or less taken as 3xn. xn is the inductive reactance to the ground. So this was basically the case where we have discussed the sequence impedances of the transmission line. So as I mentioned in the beginning, that in this particular course we will talk about the sequence impedances of the Y-connected loads, transmission lines, rotating machines, and transformers. So now we have covered the Y-connected loads, also the transmission lines. Now we will talk about the rotating machines, for instance synchronous generators. So now let's take the case of the synchronous generators and discuss the sequence network. So now this is the case of the synchronous generators, three-phase synchronous generator, where the neutral point is again connected to the ground through the impedance Zn. So now each phase is also have a certain impedance that is represented with Zg. So this is basically Zg. So that is, in each phase we have the impedance Zg, and this is the impedance to the ground, which is Zn. And we have three phase currents, Ia, Ib, and Ic, and then the current through the neutral is In, which you now In is a sum of three phase currents. That what you now from your previous knowledge. So now let's talk about the sequence networks of the loaded synchronous generator. So one can see here that the EMFs or the generated, let's say, voltages is it's a written in a matrix, where this E represent this particular matrix. And if you remember, in a balanced system, if we, let's say, take EA as a reference, then the other two phases, which are EB and EC, they will be shifted by 120 degree. And if you remember, we discussed about an operator A, and we discussed that it is equal to 120 degree. So this operator A, whenever multiplied with a phasor, it rotates that phasor 120 degree anti-clockwise. So now as you now that in case of, let's say, this particular case, let's say if this is EA, that will be the K, this will be EB then, and I believe I think I had drawn it a bit, but anyhow, this representation where we have this, I think, should have been somewhere here, but anyhow, the angle, although I have not drawn it very properly, but you know that if this is EA, this will be EB, and that will be EC. So all the three are shifted by 120 degree. So that's why we have a 120 degree angle here, and we have an angle of 240 here. So that's why EB is equal to E square EA. So we also discussed that A square is equal to 1 angle uh, mm, 240, which is also equal to minus 120. But anyhow, we have already carried this discussion before. So now uh, these three phasor can also be written as a matrix where we have an operator a square. This operator is a square because when it is multiplied with EA, it will shift this quantity by an angle of 240 degree in the anti-clockwise, and we will get EB. And when we multiply EA with the operator A, we will get a shift of 120 degree. So I mean the three voltages can now be written also. I mean where we have taken EA as common, and this is the matrix having the operator A and A square, and I mean 1 because this is the same quantity. So now I mean we can also write this matrix where we have three voltages, and it can also be written in this way as well. So now the line to ground voltages, which are basically from this point to the ground. So the line to ground voltages, we are discussing about the sequence networks of the synchronous generators. So now we are taking about we are taking the case of the line to ground voltages VA, which is also equal to VAG. So now if one look to this particular circuit, VAG will be equal to EA minus IAZG minus INZN, which is written here. So VAG will be equal to EA minus IAZG minus INZN, which is written here. So EA minus IAZG and minus INZN is equal to VA. Similarly, we can write the expression for the other two voltages, VB and VC. So now we have, we are talking about the voltage from this point to this point, which we represent with VA, from here to here VB, and from here to here VC. So this is the induced voltage, and this is the terminal voltage. This is what I would like to say. Okay. So now, as I mentioned, the neutral current is equal to the sum of the three phase currents. So putting the neutral current as the sum of these three currents, we can get this particular matrix. We have already discussed about the expressions when we considered neutral current as the sum of the three phase current. We have already discussed about those matrices, so I will not once again go through them, but if you are interested, you can put the currents neutral current as the sum of these three currents, and then you will come to you will see that it will reduce into this particular representation. So now VAG, VBG and VCG, which are the voltages from point A, B and C to the ground, can be written as EA, EB, EC, which are voltages, induced voltages or generated voltages EA with respect to the ground. So VA is the voltage, VA is the voltage from point A to the ground, and EA is the voltage that is generated with respect to the ground. So this is EA, EB, EC minus this particular matrix involving the terms ZG and Zn. So this is what we call the impedance matrix, and the matrix on the right side represent the phase current. So these are phase currents. And if you remember, we discussed that if you want to convert, let's say, phase voltages into sequence voltages, or phase voltages can be written as this transformation matrix A and the sequence voltages. We have already discussed these expression quite in detail. So now I will make a use of that, and correspondingly we can write the phase voltages or the voltages from point A to the ground as a product of, these voltages can be written as a product of transformation matrix A and sequence voltages. Similarly, for this particular matrix involving EA, EB and EC, which are the voltages, generated voltages with respect to the ground, it can be written as transformation matrix A and sequence voltages that of the E. So this case is this one. And once again, the phase current can be written as transformation matrix A and sequence currents. So we have already carried this discussion. I don't need to go into the details. So now this matrix has been written as A Vs, and this matrix has been written as A Es, and also the phase currents are written as, the phase currents can be written as, A Is. We have already discussed it. So now for each matrix, if we replace them with these expressions, we get basically on this side Vs. First we have obviously this term, then we have Aes minus Zp, which is the impedance matrix, into Ais, which represent the phase currents. So now, taking inverse of the transformation matrix on both sides, we will get now Vs, sequence voltages, equal to Es minus A inverse impedance matrix into transformation matrix Is. So now these three, a product of these three is reduced to what we call sequence impedances. So now let's derive the Zs, and then we will get the sequence network. So Zs will be, as I mentioned, it's equal to the product of the multiplication of the inverse of transformation matrix, the impedance matrix, and the A matrix. So we have discussed the inverse of the transformation matrix, which is equal to this matrix 1 over 3. This represents the inverse of the transformation matrix. This is the impedance matrix, which is Zp, and this is the matrix A. So now taking the multiplication of these three matrices. Once again, I don't need to go into the each step, but rather I am writing the final matrix, which is now equal to this sequence impedance is now equal to Zg plus 3Zn. And if you remember, this is exactly the same what we have discussed for the case of the Y connected loads, when we consider also the connection of the neutral point to the ground via this impedance Zn. So the same case, this is a diagonal matrix where the off diagonal terms are 0, and Z0 is equal to, because this is the zero sequence impedance, that will have zero sequence impedance, positive and negative. So Z0 is equal to Zg plus 3Zn, and Z1 is equal to Zg, and similarly Z2 is equal to Zg. So now we have already discussed about this matrix. It's the same what we have get for the case of the Y connected loads. So now this is the zero sequence impedance matrix. So Z0 is equal to Zg plus 3Zn, Z1 is equal to Zg, and Z2 is equal to Zg. So that's what is the sequence impedance matrix. But in practice, actually, it is mentioned here that in practice, as one can see, both Z1 and Z2 are equal to Zg, which means Z1 is equal to Z2. From that one can get that Z1 is equal to Z2. But in practice, Z1 is not equal to Z2. That is the practical case. Maybe observations are made, or measurements, or deep studies may be made where it has been found that Z1 is not equal to Z2, meaning to say that the positive sequence impedance is not equal to the negative sequence impedance. And usually in the circuits that we will solve, we will solve circuit later on in other lecture, not in this lecture but in the other lecture, when I will solve, let's say, single line to ground faults. So we will analyze that case. So in practice, usually Z1 is taken approximately either as XD. This is the, if you remember, this is the steady state reactance, the transient reactance, and the sub-transient reactance. So Z1 can be approximately taken, either of these values. And Z2 is approximately taken as the sub-transient reactance. And Z0 is taken as the leakage reactance, which is approximately equal to 0.1 to 0.7 times the subtransient inductive reactance. So as I mentioned that theoretically we have found that Z1 is equal to Z2, but in practice Z1 is not equal to Z2. Z1 is usually taken as either of these terms. As we have discussed that it is the steady state inductive reactance, this is the transient inductive reactance, and this is subtransient inductive reactance. And Z2, which is the negative sequence impedance, is usually taken approximately equal to subtransient inductive reactance, and Z0 is taken as the leakage reactance, which is approximately equal to 0.1, within this range, 0.1 to 0.7 times XD double prime, which represents the subtransient inductive reactance. So now we have determined the sequence impedance matrix, and now let me once again now write this particular expression. So now we will have the case where this is the we will have the case where we have let's say we have the let me put this particular case, and as I discussed that if you can look here, then this is the sequence these are the sequence voltages with respect to the ground from the terminal to the ground, and this is the generated voltage with respect to the ground. So now as we have determined this sequence impedance network, so now I will write this particular case as, once again, Vs equals Es minus Zs and Is. So Now let me write it again. So that is equal to V naught, V1 and V2 equal to E naught, E1 and E2 minus Z naught, uh, 0 0 0 Z1 0 0 0 and Z2 multiply with I naught, I1 and I2. So now we can determine the three sequence, or we can write from this uh, expression that V naught is equal to E naught minus Z naught I naught, because other two terms are 0. So that will be equal to Z naught I naught. Similarly, V1 is equal to E1 minus Z1 I1, and V2 will be equal to E2 minus Z2 I2. So that now we can draw three sequence networks, but we know that generators are designed to supply three-phase balance voltages. That's what we know. So taking this fact into consideration, that generators are designed to supply three-phase balanced voltages, what it would mean that, and in general, in the system what we have studied so far, we have ABC sequence or a positive sequence. So if it is a balanced and it's a positive sequence or ABC sequence, then it would mean that we will have only positive sequence voltage, that is E1, and the zero sequence and negative sequence voltages will be equal to 0. We will have only positive sequence voltage. So let's now take this case that E naught and E2 are 0, and we make E1 equal to EA, or this is another notation, but anyhow this is E1, we put it equal to EA, which represent now the positive sequence voltage. So now putting in these expressions, now putting E naught and E2 is 0, so this is 0, this is also 0, we can draw now the three sequence networks. So now this will be the case. We have this is the positive sequence network where V1 is equal to, as one can clearly see from here, V1 is equal to EA minus I1 Z1, which is the case here. It's quite clear. You know that this is quite simple. So, and if we would have, let's say, placed let's say E2 here, so that is 0. So that's why we straight away make it 0. So now V2 will be equal to minus I2Z2, because the E2, which let's say if we suppose in the beginning, if we draw based on these expression the networks and then we put it equal to 0, obviously, which means that we connect it to the ground. So let's you draw the networks based on these expressions and then you put it equal to 0. So this will be the case. V2 is equal to minus I2 Z2, no 0. So this is basically 0 because this represents the 0 voltage. And similar is the case of the zero sequence network. But important is that now we have Z node equal to Zg plus 3Zn. This is important. We have already discussed it now. So now these two are zero negative sequence networks and this is the positive sequence networks. So note that when the neutral is grounded through an impedance is Z, and we have already discussed it before. Because In is equal to 3 I naught, In is also equal to, as I have discussed, In is equal to IA plus IB plus IC, and this is also equal to 3 I naught. So In is equal to 3 I naught. In the equivalent circuit, which is this one, the neutral impedance appear as Zn in the path of I naught. So in the path of I naught, 3 Zn will appear. But in the path of In, only Zn will appear, because In is equal to 3 I naught. So we discussed this point even before. So once again, if one look here, in the positive and in the negative sequence network, Zn does not appear. Zn only appear in the zero sequence network. So we have already carried this discussion before, and it is also visible here. So now to make some important observation, which we even discussed before, but let's once again summarize those important observations, are that from the discussion we have already carried, now we have derived the three sequence networks of the loaded synchronous generator. Generators, these are rotating machines. So now we have derived we have discussed about the three sequence networks of the synchronous generator, and the conclusion or the important observation that we can now draw are the three sequences are independent. We even discussed this point before, that these three sequence networks are uncoupled. They are not dependent on each other. The positive sequence network is the same as the one line diagram used in studying balanced three-phase currents and voltages. Obviously, this diagram is exactly the same, because we are considering the positive sequence case. So this is the same as the one line diagram used in studying balanced three-phase currents and voltages. Only the positive sequence network has a voltage source. That's what we have observed here, that only this network have a voltage source. Therefore, the positive sequence current causes only positive sequence voltage drop, which is quite obvious. There is no voltage source in the other two networks, which are the zero and negative sequence networks. Negative and zero sequence currents cause negative and zero sequence voltage drops, quite obvious, from these two sequence networks. The neutral of the system is the reference for positive and negative sequence networks. So for the positive and for the negative sequence network, neutral is the reference point, but ground is the reference for the zero sequence networks, because this Zn only appear in the zero sequence network. Therefore, the zero sequence current can flow only if the circuit from the system neutral to the ground is complete, and that's what we even discussed before when we were discussing the case of the Y connected load. That if, let's say, the neutral point is not grounded, let's say, take me that case again. So we discussed that if, let's say, the neutral is not connected to the ground, then the zero sequence current will be zero, because then the impedance will be infinity. We discussed that before. So the zero sequence current can flow only if the circuit from the system neutral to the ground is complete. If, let's say, the neutral is not grounded, zero sequence current will be zero. The grounding impedance is reflected in the zero sequence network as 3Zn, which we have observed here. We discussed that before. The three sequence systems can be solved separately, because they are not coupled. They will be solved separately on a per phase basis. The phase current and the voltages can be determined by superposing their symmetrical components of current and voltages respectively. So we solved them separately, and then the results will be combined, what we call superposition, to get the final results. So these three networks are uncoupled, and they will be solved independently or separately. So now with this I would end this lecture, and I would once again say that we have now even covered the rotating machine, and we have discussed about the case of the synchronous. We have discussed um, the sequence impedance of synchronous generator, and the observations once again are that only in the positive sequence network the voltage source is there. In the other two networks there are no voltage sources, because we are considering the case of the balanced three-phase voltages. And since with the system we have positive sequences, ABC sequence, that's why only in the positive sequence we have voltage source. In the other two networks we do not have any source. And the other important point is that the zero sequence current, it only will flow if the neutral point is connected to the ground through the impedance. If the neutral point is not connected to the ground, the zero sequence current will be zero. So this is important. And also that positive and negative sequence current do not flow through the zero sequence impedance. So with this now I would end this lecture, and we will start the discussion on the transformer in the next lecture. So with this I would end the lecture, and once again I would say thank you very much for your attention, and inshallah see you in the next recorded lecture. Assalamu alaikum wa rahmatullahi wa barakatuhu.